This video is on the displacement formula. What is it and where it comes from? When you finish this video, you should be able to describe what the displacement formula is, how it can be derived, and how it can be used. Let's start by considering this problem. As you make your way to school one day, slowly walking 3 meters per second, you hear a dog barking and look around to see it chasing you. You increase your walking speed by 1 meter per second for the next block, about 100 meters. For how long does the dog chase you? Now, one of the ways we might consider starting this problem is by making a velocity time graph. Here's our velocity time graph. And here we are at 3 meters per second. And we know we increase our velocity. And we know that the area underneath this graph is 100 meters. On the other hand, we also know that the acceleration is 1 meter per second. That is the slope of that line. However, none of that is sufficient to quickly or directly get at the amount of time. For example, you might consider saying that the area is equal to 1/2 base times height, and the area is equal to delta x, 1/2 time times velocity, final minus 3. Here's the final velocity. But we know neither the final velocity nor the time. You might consider using the acceleration formula, like that. But again, we do not know the time, which is what we're being asked for, or the ending velocity. Now, it's possible, and I will try to show you, that we could combine these two things together to end up. After all, we have two equations and two unknowns. That should be sufficient to find either one of them. However, in general, we will not be doing that sort of algebra in this physics class. So instead, what I'd like to do is take you to another chart that shows data for this particular problem. Here is we've seen this sort of table before. This is a table that shows acceleration, time, velocity, displacement for the interval, displacement total, and I brought the time back over here so we could see that. And what I'd like to consider doing is making a position time graph with this data in it. In other words, along the time axis we put in 1 through 7, and along the displacement axis these numbers here. And if we did that, we would find something like this, where the slope of this early on, the slope here would be 3 meters per second, the initial velocity. Now, wouldn't it be neat if we had an equation for this line? Well, in fact, if you were to plot this data into your calculator and choose a polynomial function in your calculator fit, you would find a formula of this form. Well, let's just start like this. You would find the equation would look like this. Well, probably you'd have x's instead of t's, but it's time along the horizontal axis. And that would be able to allow you to predict how much time it would take for you to run that block as the dog was chasing you. Now, if we look at this more carefully, we'll see that 100 is our displacement. That's our initial velocity. And this is actually 1/2 of our acceleration. And so plotting the data here actually gets us a formula which is called the displacement formula. And it's a very useful formula when given just the right kinds of information. And so this formula Okay, so again, this formula here is called the displacement formula, and it's a generally useful formula and one that you will find useful and will be able to use in addition to the definition of average velocity and the definition of acceleration. Now, what I want to show you is that this formula doesn't just come out of some made-up data, but it can come out, be derived in other ways also. Let's go back to this page. Notice that this graph, I guess I'm going to redraw this here for you. Notice that this graph is really made up of two sections. There is a triangle and a rectangle. Alright, so this triangle has area or displacement equal to 1/2 base times height, and in specific terms here, 1/2 time times the final velocity minus the initial velocity. And the lower part here, the rectangle, has area. Let's do that over here. This is the lower part. Has area base times height, or VF times T. And so together the displacement of the whole motion will be VIT from here and 1/2 VF minus VIT over here. Now, I want to look carefully at this part here, because what we're going to do is use the acceleration formula, and notice, try that again, and notice that VF minus VI is equal to AT. Not surprising. And so I'm going to replace that there with AT, and the new combined formula, if you will look like this: VIT plus 1/2, substituting an AT there, times T, or T squared. And again, now we come up with, from this graph of the velocity time graph, we come up with the area underneath there equal to VIT plus 1/2 AT squared. Again, that's the displacement formula. So there's another way we can see the displacement formula being arrived at, and that is through the area under the graph. I'm going to show you a third thing here. Here's our, I've come over to a new page. Here's our graph and motion equations from that problem that I showed you earlier. And now what I want to do is to take this equation here and this equation here and combine them together. Do that algebraically. And so I'm going to take the acceleration equation, Vf minus Vi over 3, and I'm going to try to solve this for Vf. And I'm going to do that and then restart the video. Okay, so what I've done is taken equation 1 and equation 2 and combined them together algebraically. First I rearranged equation 2 to get this. I rewrote equation, and after substituting all of this, generalizing this, then I substituted 2 into 1. Looks like this, 1/2 t. Took this stuff, since that's equal to AT, substituted AT in there plus VIT. Then I simplified, and I once again come up with the displacement equation. So you've seen 3 ways that we can arrive at the displacement equation: by creating data from our knowledge of acceleration and velocity, by looking at the velocity time graph, and by doing algebra on our acceleration equation and area under the velocity graph. Alright, and the very last thing I'd like to do is to show you how we might use that to solve the original problem. So here's the original problem. I have a lot of other things here I'd like to group and get out of the way, so we'll just slide that up over here. Then let's come up and write down the displacement formula. Plus 1/2 AT squared. Alright, so in this case we have 100 meters of displacement, 3 meters per second of initial velocity times our time, plus 1/2 of our acceleration times our time squared. Now, if you try to simplify this, you'll find you have very little luck. This is in fact a second-order polynomial, otherwise known as a quadratic equation. So in order to solve this, you'll need your quadratic solver. And of course, knowing what you know about math, the quadratic will give you 2 possible answers. So if you'd like, you can plug those into your calculator and come up with a quadratic formula, or you can just take the answers that I get for you. After using a quadratic formula, you get either about, oops, let's get that out of there. You get either about 11.5 seconds or negative 17.5 seconds. Of course, time can't be negative, so that makes it obvious that the correct answer is 11.5 seconds. And that's how you use the displacement formula to solve this particular problem. Again, it makes it fairly straightforward, fairly simple, but it's important from my perspective that you understand where this tool comes from, and that's what most of the video has attempted to show you.